In this second video, we're going to take a closer look at the bromonium ions that form when you react bromine with an alkene. So let's start here by drawing our arrows for our bromine addition. The double bond attacks one of the bromines. That bromine lone pair comes back and adds to one of the carbons of two carbons of the double bond, and we have to kick out the other bromine as a bromide anion. So let's have Oscar draw that for us. So here's our bromonium ion. Now this bromonium ion is not symmetrical. There are two methyls on this side, one methyl on that. And that turns out to make a big difference. The reason is that these bonds are not all that strong. They have a lot of strain in the ring, and there's a lot of ionic character in the bond. And indeed, one can draw other resonance forms of these ions. One can draw a resonance form where you put the positive charge on each of the carbons in turn. So let's move that bond back to the bromine. That'll make a carbocation at this position. So I can draw that out. This is just a resonance form now. So let me rearrange that. So that bond's gone. The bromine now is gained 2 electrons, so it's now neutral. Sorry, gained an electron, so it's neutral. Let me go fix that. It's neutral, and the positive charge is now on the carbon, so it's a carbocation. So that's one resonance form, and of course one could draw the arrow the other direction, and let me draw that resonance arrow here just to emphasize this. There's another resonance form, okay, which would just be the other direction, where again, let me get rid of the positive charge there. I erase the bond on the other side and put the positive charge here on that carbon. Now let me move the bromine a little bit so you see the positive charge is indeed on the carbon. So now we have 3 resonance forms. Which of these is most important? Well, the bromonium ion is the most important one. This is the best representation of the molecule, but these are important contributors. And the important thing is that they show you where the center of the positive charge is on the carbon framework. The resonance form that looks like a tertiary carbocation is definitely more stable. And what it says is that if you're going to open this bromonium ion, you're going to attack at the carbon with the most positive charge. So if this other bromide is going to come in here, okay, this bromide is going to attack at this carbon, not that one. So it'll open up the ring that way. Now, opening up the ring that way gives us a particular dibromide, but in this case they're both bromine, so it doesn't really matter. But what happens if instead of a bromide there, we have water molecule? So let me erase all this. Okay, and let's say this whole reaction was taking place in water. Well, the only difference is, of course, is that the bromide would not be doing the attacking here. A water molecule would be doing the attacking. So let me put the water molecule over here, and our mechanism would simply have the water now attacking at this carbon, not that one, because this is the one at the center of positive charge. And so when we open this guy, we're going to get the water molecule on the more substituted carbon. And so the rules are basically very similar to what we saw when we were adding HBr, except in this particular case, it's the bromine which is acting as the acid. So it's like adding a Br plus to the least substituted carbon, adding the water to the more substituted carbon. So we get our bromohydrin down here, and the bromohydrin we get is the one where the regiochemistry has the oxygen on the more substituted center, where the more stable carbocation, the center which would have been the most stable carbocation, the bromine on the least substituted, the one which would form the least stable carbocation.